Okay, so today we are talking about linked lists. So basically, up until this point, we have had exactly one way of storing large amounts of data internally in a program, and that has been an array. We also talked about vectors, but really a vector is just an array when you look behind the scenes. So today we're going to be talking about a completely different strategy for storing large amounts of data called linked lists. And basically the idea is that instead of having all of the data be in one contiguous area of memory, what we're going to do is we're going to have each piece of data in our container include a pointer to wherever the next piece of data is. So that's going to look something like this. This is an example of a linked list with 3 items in it, 47, 19, 62. So here's our variable list. List is, so this is a struct or a class. In our code, we're going to be using a struct. I believe in the textbook, he uses a class, although I'm not totally sure about that. In most textbooks, they use a class. We're going to be using a struct. But anyway, we're going to call it node, and it's going to be combining 2 variables together. One variable that represents the data that would normally be like in an array if we were using an array. And then the other variable in the struct is going to be a pointer to the next node in the linked list. And right, so this struct is called a node, struct or class. So we've got 3 nodes in this linked list. That's basically the idea right there. You know, in one sense, I could stop there and say, okay, now I've told you everything you need to know about linked lists. Now go write some code. I won't do that to you. We'll be spending a lot of time actually producing some code ourselves, so you get some practice with it. But as far as the concepts go, that's pretty much it. Anybody want to ask a question about this? So you'll notice that these nodes, when we create these nodes, we do it using the new operator. So that means that the computer can give us memory from any place on the heap. So that means that the location of these nodes is pretty much arbitrary, right? They could be just scattered all over the heap, theoretically. I guess just one other thing to point out is that when we get to the last node in the linked list, the next data member of this node is null pointer, and that's how we indicate that we are at the end of the list. So we have to have some way of saying, okay, this is the last node in the list. The way we do that is we make the last node in the list equal to null pointer. Okay, any questions? So before we dive into the code, let me just talk a little bit, and you could think of this as a digression, I guess, but it's important. Let me talk a little bit about the sort of the upside and the downside to using a linked list versus using an array. So first, let's think about, let's say we've got 1 million items in our container, or we've got more than 1 million items in our container. And let's say that we want to access the 1 millionth item in our container. How are we going to do that if we're using an array? And how many steps is it going to take? Anybody want to take a shot at that? I'll give you a hint. That's not a hard question, right? We all know how to access elements of an array. Every, Everyone's being bashful today, I guess. Okay. Well, we would just use square brackets and index the array, right? So array sub 9999999 is how we would access the 1 millionth item in an array, right? And that's just one step. So that's pretty good. So I'm gonna call that array access, and I'm gonna say that in terms of a mathematical function that models the efficiency, or the models the number of steps that it takes to accomplish this task, I'm going to call that constant, right? It doesn't depend, like if we were writing a function to specify how many steps this takes, it would not depend on the size of the container or anything like that, right? So I'm going to just call it constant. What about linked list access? If we want to access the last or the 1 millionth item in a linked list, there's no way to get there directly. What we would have to do is we would have to start at the beginning of the list and just move on down the list until we get to the 1 millionth item in the list. So that's a real big downside. And we will call that a linear, because if we were to write a function to figure out how many steps that takes, it would depend on how many items are in the linked list, right? Or which item in the linked list we are trying to access, or something along those lines. Don't worry too much about the math here. If it doesn't make sense, that's okay. I'm just kind of trying to give you a sneak preview of what you'll be talking a lot more about in your future classes. So that's bad, right? That's a downside to linked lists. Another downside to linked lists is that we'll be using a bit more memory, right? Because every single piece of data has a pointer attached to it, which is something we don't have with an array. That's usually not a big deal though, but I'm just throwing it out there as a second downside to using a linked list instead of an array. So why would we ever want to use a linked list instead of an array? Well, let's think about if we have a container with 1 million items in it, and we need to insert something at the front of that container. Okay, I'm just going to tell you, and we're going to see this in a minute. So I might be doing this a little bit out of order, but I'm just going to tell you that the way to insert an item at the beginning of a linked list is we're just going to create a new node. And then we're going to move our pointers around, right? We'll just make list point to this to make it, so, whoops, that's not what I meant to do. So to make it the first node in the container, and then we'll make this guy point to the what used to be the first item in the list. So hopefully you can see from this picture now that in just maybe 2 or 3 steps, I have inserted an item at the front of my container. Okay, so that's constant. Doesn't matter how many items there are in the linked list. It's just going to take me 2 or 3 or 4 steps to insert something. Okay, I'm gonna erase all those edits that I just did and go back to our original picture. Oops, forgot that would be. So linked list insert constant. Okay, what about if we've got an array with 1 million items in it and we want to insert something at the front of the array? Any thoughts about how we would do that or how many steps it would take? Okay, so we imagine you've got a big array with 1 million items in it, and I want to insert something and make it the first item in the array, the only way to do that without rearranging all of the order of the rest of the items in the array, I guess maybe I should have specified that, is that we're going to have to shift all of those 1 million items down one so that we get the first spot in the array available to put our new value in. Does that make sense? Anybody want me to draw a picture of that? If that's a little fuzzy, I think that should be pretty clear, right? Picture an array, and then you will need to insert something at the beginning of the array. The only way to do it is just to shift everything down so you can stick the new item in at the beginning. So array insert is linear. Okay, so whether you want to use an array or a linked list depends on what you're going to be doing a lot of, right? If you're going to be doing a lot of accessing and not very much inserting, then an array is better. If you're going to be doing a lot of inserting, and I might add deleting, and not so much accessing, then the linked list might be the better choice. Okay, so that's the process there of deciding what structure to use in a particular application is super, super important. Something that, you know, maybe the most important thing that you do in your data structures class, deciding which data structure to use in a particular application. Okay, so that was kind of a long digression. Not important that you understand all of those details at this point, especially the math, but just wanted to give you at least have some idea of why we would ever want to do something like this instead of just using an array. Okay, I think we're ready for some code. Let me pull up a client here. So here's a client program. It's actually sort of long. And so basically what we're going to be doing for the next couple of lectures is just uncommenting this client code one step at a time each time we add a new member function to the class. So I am calling our class simple list just because, you know, I'm trying to keep it simple. I'm not going to have, I'm not going to make it templated. I'm not going to have iterators, anything like that. Just going to try to keep it simple so we can focus on the linked list manipulations. And so basically what I've got in my client program at the beginning is we're going to need a constructor. We're going to need an insert function, and we're going to need a print function. 3 functions, and then we will have enough so that we can test our class and see if it's okay so far. All right, here's our header file. You'll see the prototypes for those 3 functions that I just mentioned. And then you'll see the declaration of the node struct. Okay, so I'm declaring a struct there with 2 data members, one named data, the other one named next, which is a pointer to the next node. Notice you'll have something that might at first look sort of circular here, right? We are using the word node as part of our definition of the word node. But this is a special case that is allowed in C++ because we're not actually declaring a node, we're declaring just a pointer to a node, so that works. And then we have our data member list, which is a pointer to a node, right? So hopefully that matches up in your mind with the picture over here. List is a pointer to a node, right? So let me make just another quick digression. There are a lot of different ways of declaring the nodes. A lot of textbooks that I've seen are going to make it a class instead of a node. A lot of textbooks that I've seen are going to make it a class that is separate from this class instead of nested inside this class. If you do that, then what that means is that you're going to have accessors and mutators for the private data members of the class. And honestly, that just makes the code quite a bit more complicated, because instead of just accessing those data members directly, you've got to say, you know, set data, set next, give it an argument, all that sort of thing. So I can't remember for sure what it does in the textbook. So I'm not going to say anything about that, but I just wanted to put that out there so that you won't be in shock if you see somebody doing it a different way. In my opinion, you know, this struct is inside the private area of the simple list class anyway, which means only member functions of the simple list class will have access to them. And I think that's perfectly safe. No need to make it a separate class with private data members. Okay, any questions about anything so far? Any questions about the code in my header file? All right, let's start with the implementation file. So first I'm going to work on my constructor. So for the constructor, we're not going to be doing much. All we need to do is we want it to represent an empty list, right? A simple list with 0 items in it. And the way that we're going to represent that is just by making the list data member equal to null pointer. So it's not pointing at anything. And that sort of makes sense. It's consistent with our strategy of having null pointer mark the end of the list, right? It's an empty list, so list is just going to be equal to null pointer. So list gets null pointer. Any questions about that? Okay, let's work on insert. So now this might be a little confusing, but I'm changing things up a little bit here. I think I'm just going to call this item instead of insert. So I'm declaring this int parameter using const ampersand. Normally, you would not want to do that. It doesn't make sense to make an int const ampersand because you can just make it pass by value. The reason I'm doing that is I want to make my code flexible enough so that I can easily change from int to something more complicated. So in case I'm going to later on, I want to change my simple list class so that it is a list of feet inches objects or fractions or whatever. I've already got everything set up for that. So that's why I'm using const ampersand instead of just a regular pass by value. Okay. So here's the steps to insert. I kind of showed them to you already, right? The first step is going to be to create a new node. So the way I would draw a picture of that would be like this. Okay, so there's my new node. And when I create a new node, normally I have a pointer pointing to it from the stack. So we're going to call that new node. New node. And so here's new node. So that's the first step. Create a new node and then we're going to have a variable, a local variable named new node that's going to be pointing at it. So hopefully by now, everybody remembers how to make this happen, right? I'm going to, the type of this variable new node is going to be pointer to node. And then I'm just going to say, make it point to, a newly allocated variable of type node. Okay, any questions about that line of code? All right. By the way, I've been seeing a lot of this lately. Whoops, not that. Try that again. This, I suspect that probably comes from Python. If not Python, then Java. But anyway, I just want to point out that in C++, that's not the correct syntax. You don't need parentheses there. Okay, so we have created a new node. Now we're going to fill in the data part. So let's say that that item is equal to 32, for example. So that means I'm going to put a 32 in there. Let me just center that. Did that work? The wrong cell. Ah. Okay. So the way that the code that does that for us is going to be this. Hopefully you can think back to the pointers lesson and remember how to do this, because I don't think we've actually practiced with it since the pointers lesson. But it's going to look like this. Node, arrow, data, not node. New node, which is the name of the variable, arrow data gets whatever the item is. So 32 in our picture. Okay, and so what that means, remember the arrow operator is the dereference and then select operator, right? So start with new node, dereference it, which means follow the pointer, and then select the data member, which is the this top data member here. Okay, any questions about that statement? You're going to see that arrow is going to be like in practically every line of code that you write when you're using linked lists. So you will get used to it. Just another reminder, this actually is the same thing as if we said that, right? So dereference new node, in other words, follow the pointer, and then dot data on the thing that new node is pointing at. This is just a much clearer syntax instead of this. It may not be obvious at this point since this is such a simple statement, but once we get into, statements that have 2 or 3 or 4 arrows in them, it's a pretty big one. So we're not going to do it this way. We're going to use the arrow. All right. Next step is I'm going to make the next data member of this new node point up to the 47. And then I'm going to make list point down to the 32. That's 2 steps really, but I just want to finish the picture there. Anybody not following how that accomplishes the task of inserting this node? Does that make sense? Make this point up here, right? And then make this point down here so that now the list goes 32, 47, 19, 62. We just inserted the 32 at the beginning of the list. Okay. I forgot to have, usually when I do this, I have a little conversation before I dive in, and I ask whether it's better to insert at the front of the list or at the end of the list, because our insert function doesn't specify, so we can insert it wherever we want. So we're going to insert it wherever it is easiest and most efficient. And it turns out that that is at the beginning of the list. Inserting something at the end of a linked list is actually very difficult because there's no way to get directly to the last node in the list. We have to start at the first node in the list, then move all the way down the list to the end, and then we'd have to insert. So that's why we are inserting at the front of the list instead of at the back of the list. All right, so I'm going to actually go back to what we had a second ago. Let me ask you this. Can I reverse the order of those statements? Can I say make list, first make list point down here, and then make next point up to the 47? Does that sound okay? Anybody see any problem with that? Okay, thank you for admitting that. So let me tell you the problem with that, okay? If you look at the picture right now, you can see there is no way for me to access this node. It's gone forever. I can't make the next data member of this node point to this node because I have no way of accessing this node. Does that make sense? So that's something that you got to be careful with when you're dealing with linked lists and pointers in general, is if you make something, if you move a pointer, you're likely to be losing what it was pointing at. So bottom line out of all of that is, starting from here, which was the original situation, we have to put this pointer in first before we move this pointer. Okay, so that's going to be a couple of pointer assignment statements. Remember, when we use assignment operator with pointers, it just means make the thing on the left point to the same thing that the variable on the right was pointing to. So the first thing I want to do is make new node arrow next point to the same thing that list was pointing at. Right? Remember when we start, we were looking like this. So that's going to be new node arrow next. Pretty much the same thing I have here, except I'm filling in the next data member instead of the data member. And I want it to point to the same thing that list is pointing at. Okay, so that says make new node arrow next point to whatever list is pointing at. Any questions about that statement? Okay, then the last thing we want to do is make list point at the same thing that new node is pointing at. Right? Okay, so just be super, super careful when you are doing an assignment statement that has pointers in it. Very, very common mistake that students make is doing a pointer assignment when they mean to actually be copying data, or actually maybe even more often the other way around, actually copying data over instead of copying the pointer. So just be careful to keep those things straight in your mind. Look at the picture that you've drawn. Decide whether you're moving an arrow or whether you are copying data. And then if you're moving an arrow, make sure that the variables in your assignment statement are pointers. All right, any questions about the insert function? Okay, let's talk about print. So I'm going to make some of this stuff go away. I should just delete that. Okay, so this is our original, not original, but this is an example of what our linked list might look like when we call the print function, right? So the basic strategy here is going to be that we are going to create a temporary pointer that's going to start off pointing at the first node in the linked list. Then we're going to have a loop where we print the node that that temporary pointer is pointing at, and then we move the temporary pointer down so it's pointing to the next node in the linked list. I guess I used the word down there, which was probably a poor choice of words, right? Since the next node is actually above the previous one. So I could say the second step inside the loop is going to be advance that temporary pointer so that it points at the next node in the linked list. So first step is to create this temporary pointer and make it point to the first node in the linked list. Let's call it curve pointer. Okay, so how do we make that in code? Anybody want to take a shot at this? How do I write the code to make that happen? Declaring a new variable named curve pointer and making it point at, or in other words, initializing it to point at the first element, the first node in the linked list. Okay, so how do we declare a pointer variable? That's a pointer to a node, right? Curve pointer is going to be a pointer to a node. So that's just node star curve pointer, right? And now I could do this on a separate line, but since I'm here, I might as well just initialize it. I want to make curve pointer point to the same thing that list is pointing at, right? So I'm just going to say curve pointer gets list. Okay, so the result of that line of code is the picture that you see. Curve pointer is now pointing at the same thing that list is pointing at. So now what we need to do is I'm going to have a loop that's going to keep going until I reach null pointer. Inside the loop, I'm going to print the data of the current node and then advance curve pointer to the next node. So while curve pointer is not equal to null pointer, print the current node. And then advance curve pointer so it's pointing to the next node in the list, right? So in our picture, that means move this down to here or up to here, however you want to say it. So in other words, make curve pointer point to whatever curve pointer arrow next is pointing to. Okay, so the result of this second statement inside the while loop is now curve pointer points at the 47. Okay, then go to the top of the loop, curve pointer is still not equal to null pointer, so print the 47 and then move curve pointer down again. Back to the top of the loop, curve pointer is not null pointer, so print the 19, move curve pointer down again, or advance curve pointer again. Curve pointer is still not null pointer, so print out the 62. Let curve pointer be equal to curve pointer arrow next. Curve pointer arrow next is now null pointer, so that means curve pointer is now going to be null pointer. Now we go to the top of the while loop and the condition is now false, and so we're done with the while loop. Still, I guess I just want to throw in an indel here. And we're good. Any questions about the print function? All right. I need to take a quick break, so I'm gonna pause the recording and I'll let you stare at that for a minute, and I'll be back in about 3 minutes or so. Okay, so we're back. Everyone hear me okay?
Yes.
All right, thank you. Okay, so I think we're actually at a point here where we can test something, right? Keep in mind, I'm modeling good practice here, right? I'm trying to write as small amount of the code as I possibly can before I go ahead and try it on a client and just see if what we've got works. And that way we're just going to incrementally add just a little bit of code, but like one member function at a time, and test it each time. Okay, so we are going to say G plus simple list client. Simple list. Okay, so I guess I should have the client up here so you can see what we're expecting to have happen. Basically, we ask the user to enter a bunch of numbers. We insert each number into our linked list, and then when we're done, we print them out. So I'm just going to enter 1, 2, 3, 4, 5, enter a negative number, and there's my linked list. Anybody surprised that they came out in reverse order? Makes sense, right? Because each time we inserted a number into the list, we put it at the front of the list. So we put 1 in the list, and then we put the 2 in front of the 1, and then we put the 3 in front of the 2, and so on. So when we're done, we've got 5, 4, 3, 2, 1. Okay, any questions so far? All right, so basically at this point, what I want to do is just start working down our client program here. Looks like the next thing we're going to be working on is a size member function. So I'm going to uncomment the code from the client that tests the size function. So just to talk a little bit about that, it's not a bad idea to actually have a data member of our class named something like num items. Probably a good idea. but we're not going to do that. We're going to write our size function so that it actually counts the number of nodes in the linked list. I want to say, yeah, it's probably typically better to have that, but not necessarily. I want to at least have you think through the fact that it's not automatically more efficient to have a num items data member that always keeps track of how many items are in the list, because every time you insert something into the list or delete something from the list, you've got an extra step now, right? You have to update the num items data member. So, you know, typically that's probably not going to be as inefficient as the process of actually having to count the number of items every time you want to know the size of the list. But I just want you to see that there is another side to it. And if you're in an application where you're almost never going to need to know the size of the list, and you're going to be doing tons of inserting and deleting, it may actually be less efficient to have a num items data member. Okay. So anyway, that was sort of a digression. We do not have a num items data member, so we're just going to count the number of nodes. And basically what that's going to look like is, let me first add it to my header file. Okay, so that's actually going to look an awful lot like print. We're going to have a temporary variable that we're going to point to the first node in the list. And then we're just going to add one to our count and move that curve pointer down to the next node in the list. Okay, so it's going to be an awful lot like print, except instead of printing the data at each node, we're just counting each node, right? So I'm going to say node star curve pointer this list, while curve pointer is not equal to null pointer. So that we're going to need a count. Then each time we get to a node and we haven't reached null pointer yet, we're going to say count plus plus, and then move curve pointer down, or advance curve pointer to the next node. Okay, and then the only other thing left is just return. All right, any questions about that? Everyone see how this is going to work. I'm creating a new node named curve pointer, pointing it at the first node. Then I've got a while loop that just says count plus plus, advance curve pointer, 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 which at that point will make curve pointer equal to null pointer. Okay, we should give that a try. Where do I have size type? Oh, no. Oh, in my client, that's right, okay. I knew I shouldn't have gone away from my notes. Try that. There we go. Okay, so I'm going to just enter my numbers again, and then it's going to tell me there are 5 items in my linked list. Okay. Okay, so I intentionally sort of did that using int so that I could separate the conversation about size type out of it. If you've got a pretty good handle on size type anyway, then switching from int to size type shouldn't be a big deal at all. If you're a little fuzzy on it, just, I guess, pay close attention again. I do want to say, I'll just admit that I'm a little conflicted about whether I should even bother teaching you about size type. I kind of go back and forth on it. So I am showing it to you. It's not like part of the core of what we're trying to learn here. Don't stress out too much if it doesn't make sense. In fact, it would surprise me if it made a lot of sense to all of you why we're using it. But I think you should be able to get a handle on how to use it, right? So in my client, instead of int, I'm going to say size type. And again, the reason for that is there's no guarantee that an int is going to be large enough to store the number of items in the container. So what that means is my size function is going to have to return size type. Well, first of all, I'm going to have to define size type. So we saw this last time, I believe. Or at least when we were studying lesson 19. If you need help with size type, you could go look at lesson 19. There's a whole section on size type. Oops, size T, size type. Okay, and then my size function, instead of returning an int, it's going to return a size type. And my client, same thing, except here I'm going to have to actually say simple list : size type for the return time. And then also actually inside here, count should be a size type. If I make count an int, then that int might not be big enough to store how many items there are in the container. Size type allow for a larger number of values than int. Technically, there's no guarantee of that. Technically, the only guarantee is that it allows for a large enough number to represent the number of items in the container. However, in practice, it typically is implemented as an unsigned int, which makes sense, right? A size is not going to be negative. And an unsigned int can store numbers twice as big as a signed int, because you get one more bit out of it. All right, you didn't need to understand all of that. If I lost you there, don't worry about it. Important thing is just to understand how to use size type. Okay, so I think I switched everything from int to size type that needs to be switched. So let's just check it again to see if we're still everything's still good. Oops, I typed it into chat instead of in the... Okay, so it looks like we changed everything from int to size type and everything is still working fine, so we're still good. Any questions about the size function? Okay, let's see what's next in the client. Oops, wrong. So it looks like the next thing we're going to do is we're going to write a function named find. And it looks like, and so I'm sort of facetiously acting as if I don't already know this, but what I'm trying, the point is that you can look at the client program to determine what the find function is supposed to do, right? I've got two arguments, a num and a found. Num is what I'm trying to find in the linked list. Found is going to be set to either true or false by the find function. So if whenever I call find, I should check the value of found before moving on, right? So if found is false, so if not found, that means that that number wasn't in the linked list. Else, I can print out the data associated with that number. Okay. Any questions about what the find function is supposed to do? I will point out one sort of potential confusion, I guess. It might seem a little bit like it's pointless what we're doing because I'm writing a find function that looks for, let's say we're looking for the number 5 in our list, right? So it looks for the number 5, and when it finds it, it just returns it, right? So that may seem kind of silly. But the point here is that in practice, what it's going to be is it's going to be like you're going to be looking for an ID number or something like that. And then there's going to be a bunch of data associated with that ID number that you're looking for. And so you'll be, what you'll be returning will be like an entire object that represents something like maybe an employee or a student or something. But I didn't want to get all complicated yet. So we're just going to return the int, very simply return the int that we find. Okay. All right, so I'm going to uncomment that. So I'm going to add a find function to my header file. So it's going to return, this is so one of the things that's simple about this list, right, is that it's not templated. So it's just going to store integers. So the return type will be int. And then there's two parameters, item that I'm looking for. And the found parameter that we set to false if we didn't find what we were looking for. Okay, and that's const, right? Because we're not changing anything, just returning something. All right, so let's go to our implementation file and define this function now. Actually, maybe I'm just going to copy and paste this in. Okay, so int, got to add our scope resolution here. Here's an important point, right? Notice that this is not a size type, right? What's being returned here is actually whatever the type of values that are being stored in the container. So I don't want to replace all of my ints with size type, just the ones that are being used to keep track of the number of items in the list. Okay, I think this looks good. All right, so we're going to do something similar to what we did with print and size. We're going to have a cur pointer. We're going to make it point to the first node in the linked list. And then we're going to keep moving down the linked list until what? Nobody wants to take a shot at it? Okay, so we're going to move down the linked list. There's a couple, this is a little complicated because there's two different things that might make us stop, right? We might want to stop because we found what we were looking for, or we might want to stop because we've reached the end of the list. So it turns out that there's a couple of different ways to write this. In the lesson, I actually show both versions. I think it's slightly, the code turns out to be slightly simpler if we just have a while loop that goes until null pointer. And then if we find what we're looking for, we just return it at that point right out of the middle of the while loop. The other option is to actually have that information in our while loop header. So we could say while cur pointer not equal to null pointer, and cur pointer arrow data not equal to item. Right, so keep going until one of those two things happens. And then after this while loop, we would have to have an if statement to try to figure out which of those two things happened that made the loop stop. So instead of that, I'm just going to say, keep going until you get to the end of the list. But then inside, I'm going to say, if we find what we're looking for, oops. Then we're going to set found to true. And we're going to return cur pointer arrow data. And then if we haven't found what we're looking for, we're just going to advance cur pointer to the next node in the linked list. Okay, so if we get to the end of the while loop, that means that we did not find what we were looking for. So we're going to set found to false. And then, set found to false. And then we need to return something, right? The compiler won't let us just leave things like this because there's a situation where we don't return anything at all. So what we should return is whatever the default value. So let me say this, whatever we return here is, it's undefined, right? Like if found is set equal to false, that means that whoever is calling this function should not be using whatever gets returned anyway. But just in case they do for some reason, we're going to return the default value for whatever the type is. So in this case, since we are just using integers, we're going to return 0. But I want to write this a slightly different way because this is something that you're going to want to get used to. So I'm going to stick with the strategy of trying to make this so I could easily change it to be a list of feet inches objects or something else instead of ints. And right, so if what I was returning here was a feet inches object, it wouldn't make sense to say return 0. I'd have to return some sort of a feet inches object. So the way we can do that is just by calling the default constructor for whatever the type is. So I'm going to say int open paren, close paren. And that just means at the highest level, that just means return the default value for int. To get a little bit more detailed, than that. What's happening there is I'm calling the default constructor for type int, which is something that C++ provides for all of its primitive types. And so in the case of the default constructor for int, what it sets the int to is 0. And I'm pretty sure we've seen this syntax at least once before, but it is a little, it can be a little confusing. Just know that what's going on there is we're actually using the constructor to actually create an integer object that is anonymous. In other words, we never give it a name, but that's what it is. It's an integer object that's being returned. All right. Any questions about any of that? I could just say return 0 there, everything would work fine. But then if I changed int to feet inches in my class, it would stop working. All right, let's give this a whirl. I will say just briefly in the lesson, you're going to see that I used value type throughout, which is actually probably a pretty good idea. I just didn't bother to do it here during the lecture. But if we had a value type defined here, and then we just used a value type everywhere in our code, then it would be very easy to later change it to something like feet inches. But you can take a look at that in the lesson if you want to. We're not going to bother with that today. Okay, someone has a question, go ahead.
Excuse me, can you go back in the C plus, yeah, this one. So right now you said like the return, we can put 0, right, over there.
That would work if we put 0, yes.
So how about if 0 is part of, how about if 0 is part of the data inside the?
Well, so the point here is that it doesn't really matter what we return, right? It's okay. I mean, we could, if we wanted to, we could say return 47 and that would work, be perfectly fine, right? Because found has been set to false. So whoever called this function should not be using the return value anyway.
Okay.
The reason that we want to use the default value for the type is just because at least that way it's not arbitrary, right? At least we're using the default value instead of just returning something random like 47.
Okay.
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 All right. So if I was using value type, this would say, so first of all, this would say value type, right? This would say value type. And this would say value type. You'll see that in the lesson. Okay, we can give this a try real quick. Actually, let me do it first and then give this a try. I forgot to declare curve pointer and I made it uppercase. Interesting. So curve pointer is just a pointer to a node. And I'm starting off setting it equal to the first item in the list. Let's give that a try. Not any better. Okay. I used uppercase sometimes and lowercase sometimes. So let's stick with all lowercase. And try again. Okay, so I'm going to insert a bunch of numbers into my list. It's going to get printed. Then I'm going to try to find some numbers. It'd probably be, you know, to be exhaustive here, I should just make sure that it works if the number I'm looking for is the first item in the list. It should work if the number I'm looking for is the last item in the list. And it should work if the item I'm looking for is not in the list, right? Any questions about any of that? Okay, so I'm not gonna do another function because we are out of time, but I do want to mention something that I just remembered I mentioned in this morning's lecture and I didn't ever get around to it this afternoon, so I just want to put it out there. One of the most important things to remember about working with linked lists is that usually there are going to be a number of special cases that you are going to have to handle, right? In our code, that wasn't true so much primarily because we're keeping things simple and just inserting at the front of the list. But typically you're going to have to be very careful and sort of have a list in your mind of all of the special cases that you want to just double check and make sure your code works for, right? So you sort of write your function for the general case, and then you say, okay, is this going to work if it's an empty list? Is this going to work if the item is not in the list? Is this going to work if there's only one item in the list? Is this going to work if I'm doing something to the first item in the list? Is this going to work if I'm doing something to the last item in the list? And so on and so on. So, and oftentimes, typically there's going to end up being 3 or 4 different cases that you're going to have to make sure you get right. So just putting that out there as something that's going to be super important when you get to doing the lab for this that goes with this lecture. Anything else you want to talk about? All right, so I will see you on Wednesday then.